Hello everyone. In this video, we'll learn how to compute probabilities associated with different probability distributions. We'll begin with binomial distribution. A binomial distribution is a discrete probability distribution, and it has two important parameters, n and p. Now, we use a binomial distribution whenever we're interested in finding the probability of x successes in n independent trials, where the probability of success in each trial is given by the number p. Now, if you think of flipping a coin, say 5 times, where each trial has, you could either get a head or tails. And suppose I define heads to be a success and getting tails to be a failure. If I'm interested in getting, the probability of getting 3 heads in 5 trials, what's the probability of getting, say, 2 heads in 6 flips of the coin? All of these are variables which could be modeled using a binomial distribution. Essentially, x number of successes in n independent trials, where the probability of success in each trial is given by the letter p. So that's a binomial distribution. So let's look at a few examples to see how to compute these probabilities using Excel. So we have an experiment here. So the experiment is one of where we are rolling a single fair die, and we know that there's equal likelihood of rolling every single number from 1 up to 6. Now let me define a random variable x to be the number of ones that we roll in 6 rolls of the fair die. Well, this variable x could take on 7 different values going from 0 to 6. Well, 0 could mean that I did not roll even a single 1 in all those 6 rolls of the die. The number 3 could mean that I rolled 3 ones when I rolled in 6 rolls of the die. And 6 is the maximum here, because if I end up rolling a 1 in all 6 rolls of the die, then I can get a value 6. So this is my random variable. And suppose I'm interested in finding the probability of rolling x number of ones in 6 rolls of the die. That is, I'm describing x successes, where the success is defined as rolling a 1. If I want to find the probability of x successes in 6 trials, then I'm essentially talking about a binomial distribution. So we're going to compute these different probabilities that this question asks using the binomial distribution. So let's begin. What's the probability of rolling exactly 3 ones in 6 rolls of the die? First, let's identify x, n, and p. So we're talking of 3 successes in n trials. The probability of success is 1 by 6. The probability of rolling a 1 is 1 by 6 in each trial, and that's what I denote by p. Probability of exactly 3 ones is given by p of x being equal to 3. And the way to compute this is to say binom.dist. So you put equal to, and then binom.dist is your function. And it has 4 arguments. The first argument is the number of successes, and that's 3. Second argument is the number of trials, which is 6. Third argument is the probability of success in each trial, which is 1 over 6. And the last argument is a true or false type argument. If I say true, then it gives me cumulative probability, which is, it computes the probability of this particular number that I've keyed in here, which is 3. And it adds to that the probability of every single number to the left of 3. So if I say true here, it'll give me the probability of getting 3 ones, plus the probability of getting 2 ones, plus the probability of getting 1 1, plus the probability of getting 0 ones. So it's essentially giving me the probability, the cumulative probability up to that particular number defined in the function, up to the particular value that we're interested in. But right now, for this question, we don't need cumulative probability, but rather what we want is our probability mass, or the particular probability at a certain given point. So I only want exactly 3 ones. I don't want the cumulative probability. So I'm going to say false and enter. And that's the answer. Probability of rolling exactly 3 ones is 0.0535. Now let's look at the next one. What's the probability of rolling at most two ones. So here I'll let you fill out these x, n, and p columns on your own. But here we're essentially asking probability of at most two ones, meaning x can take on a maximum value of 2, but it could be, so x could be 2 plus x could be 1. It could be lesser than 2 as well, right? Plus x could be 0. So essentially, I'm asking for probability of x being lesser than or equal to 2. Well, now we've written this down in a form which is very similar to how we'll write down a cumulative probability function. So I want the probability of getting a 2 and and I want to add to this the probability of every value to the left of 2, which is probability of x being 1 and probability of x being 0. Now this can be very easily done in Excel. Binom.dist. I want 2 successes in 6 trials, 1 in 6 chance of success, and I'm going to say true to cumulative because I want the cumulative probability. When I press enter, I get this answer. Now I can actually check if this is indeed the correct answer by manually doing it in the long way. So which means I want to do binom dist of 2 successes, 6 trials, 1 in 6 and false, plus binom.dist 1 success, 6 trials, 1 in 6 false, plus binom.dist 0, 6, 1 in 6 false. The answers are the same. So this is a much quicker way of finding the answers. Let's try the next one. Probability of rolling more than 4 ones, meaning probability of x being greater than 4. Well, I want to try and get this to be in the same, in a notation which is very familiar for Excel, which is I wanted to get it to be in this lesser than or equal to form. And for that, I'm going to use the power of complements. So the probability of x being greater than 4 is 1 minus the complement of x being greater than 4, which is x being lesser than or equal to 4. And why do I write that? Well, x being greater than 4 is actually x being equal to 5 plus x being equal to 6. Now, I know that the sum of each of these probabilities has to add up to 1. So instead of just counting 5 and 6, I could take 1 and remove the probability of all the values from 4 and below, right? So I could take 1 and remove probability of x being equal to 4, minus 3, minus 2, minus 1, minus 0. And that is essentially what I'm doing when I write it down this way. And when I put it down this way, I can easily type in Excel's function and use the cumulative probability and compute the answers. So the answer is it's going to be 1 minus binom.dist. Oops, sorry. Yeah. We're looking at 4, 6, 1 by 6, true. And that's the answer. I'm going to encourage you to do this on your own using the long way and check if your answers are right. The next one is a little bit different. We want the probability of rolling at least 4 ones in 6 rolls of the die. So probability of x being greater than or equal to 4. Well, the probability of x being greater than or equal to 4 is x could be 4, plus x could be 5, plus x could be 6. So if I want to rewrite this greater than or equal to 4 using the complement notation, I'll say the complement of being greater than or equal to 4 is to be less than 4. Oopsie, sorry. Less than 4. But this is still not quite in the cumulative distribution type that I'd like it to be. So can I rewrite this as 1 minus p of x being lesser than or equal to? So, and this is exactly nothing but, if I subtract the probability of all values 3 and below, then I'm left with 4, 5, and 6. And these two are equivalent expressions. And therefore the answer is 1 minus binom.dist 3, 6, 1 by 6, true. That's your answer, and I'll encourage you to compute this in the long way and check as well. Now in this video, I'll go over one more example, and I have left another third example here in the spreadsheet for you to try out. So let's check the second example. The probability that the San Jose Sharks will win any given game is 0.3694 based on a 13-year win history. So if I'm talking about winning or losing, it's a binary outcome, and we're given the probability of success to be 0.3694. An upcoming monthly schedule for the San Jose Sharks has about 12 games. Now, we want to find the probability that, what's the probability that they will win exactly 6 games in that upcoming month? So we could think of 12 games as 12 different trials. The probability of winning any game is 0.3694. So the probability of success in each trial is 0.3694. And we want to find the probability of exactly 6 successes. So we want 6 successes in 12 trials, 0.3694 as probability. So I want P of X being equal to 6. So here, this is nothing but binomial.dist. 6 successes in 12 games, 0.3694 is the probability of success in each game. I don't want the cumulative function, I want probability mass function. That's the answer. The next one, probability that they will win at least 5 games in that upcoming month. So this is going to be, so we're going to do something very similar to what we did right here. So let's try that. At least 5 games is X being greater than or equal to 5, which I could write as its complement of X being less than 5, which I could rewrite as 1 minus probability of X being lesser than or equal to 4. So this way, I'm counting off, I'm subtracting all probabilities for values 4 and below, and therefore I'll be left with the probabilities of numbers 5 and above. Therefore, this is 1 minus binomial.dist 4, 12, 0.3694 and false. Sorry, this needs to be true, not false. And that's your answer. So I have one more question here, and I'll let you solve that. And what I'll do is maybe put the answer down here so that you can quickly check. So the answer, I'll put this in the spreadsheet when I upload. So happy solving. I'll see you in a different video.